In activities 2 through 5, students will use Kinects to build cars that are powered in a number of different ways. In activity 2, their engineering design challenge will be to build the fastest gravity-powered car they can. On the way, they'll learn concepts of friction, how to measure speed, and also the concept of design specifications.
Students should be encouraged to be as creative as possible with their car designs. The instructions for the prototype are given in the youth handout. However, since this is an engineering activity, students should be encouraged to either modify this design, or if they want to build their own from scratch. If students decide to do this, however, they should be aware that there are a number of requirements that must be met. For example, in every car there must be a cross brace at least 3.5 inches from one of the axles. In addition, the spacing of the tires must be between 2 and 5 inches. These rules may seem arbitrary, however, in the next activity, the students will be adding rubber band power to their cars, and these requirements must be met. So a small car like this, even though it may perform well on the ramp, does not meet the requirements of this activity. Be sure that the students read and fully understand the design constraints before beginning so that they do not have to start over.
To test our cars, we'll need a ramp. Now you can do this inside by placing a large piece of cardboard up against a box or chair. Or if you'd rather go outside, you can find a sloped sidewalk or a wheelchair ramp. The first step is to take a piece of tape and mark the starting point. You can also use chalk if you'd like. If you're using cardboard, you can just use markers. From the starting point, we measure anywhere from 36 to 100 inches as the length of our ramp. I'm going to use 75 inches. We place another piece of tape as our finish line. Once we have our ramp set up, we can test our cars. To do this, we first place the car at the starting point. As soon as we let go of the car, we start the stopwatch. We stop the stopwatch as soon as the car crosses the finish line.
In this activity, the challenge for the students is to make their cars go down the ramp as fast as possible. Remember, speed is defined as distance divided by time. While on the ramp, the car's speed is constantly changing. However, we can calculate its average speed by taking the total length of the ramp and dividing it by the time it takes to go from start to finish. For example, if your ramp is 75 inches long and your car takes 3 seconds, its average speed is 25 inches per second. This activity should be a process of trial and error. Students should test their cars, and then if they see fit, they can make modifications. Then they should test their cars again to see whether or not their modifications improve the performance of their cars.
As an alternative, you may choose to have the students measure their car's speed after it reaches the bottom of the ramp. This is an especially good idea if your cardboard is not very large. This is done in pretty much the same way. The main difference is that now you'll need 3 markers or pieces of tape. The first marker is on the ramp and it shows students where to release their cars. The second marker is at the bottom of the ramp and shows students when to start the stopwatch. The final marker is a short distance off and shows students when to stop the stopwatch. Students will release their cars at the first marker, start the stopwatch when their car reaches the second marker, and stop the stopwatch when their car reaches the final marker. Speed is calculated in exactly the same way, using the distance from the second to third markers divided by the time it takes to go between the two.
For each of activities 2 through 5, when we're processing the activity at the end, it's important to bring the students back and have them think about which design modifications worked well and which didn't. For each of these engineering design challenges, you can use the same set of questions to process the activity. Start by asking the students which designs they built worked best and why. Those groups that worked well, or even those people who saw groups working well, can usually identify a couple of things that made the cars work better or not so good. Then, you might ask them which cars didn't work so well and why not. In this instance, in activity 2, those cars that had a lot of friction in their wheels may not have moved so well. Finally, it's always good to ask the students, what would you do to improve your designs? All engineering designs can stand improvement, even many of the ones in production, And so it's great for the students to think about what ways can their designs be better. None of these cars are going to be perfect.